including you. So,
Sir, I've started the recording.
Okay, yes. Mm, So, can you share this? Yeah.
yes, sir, I am. Wait, sir. Sir, which slide should I go?
Uh,
Slide?
so you go to the presentations. Yes, you go to the presentation and then go to the second experiment, that is emissivity. Not the yes.
Yes, sir.
So you go to the emissivity. So can you all hear me?
Yes, sir.
Yes, sir.
Yes, sir,
Okay.
you're audible.
Okay, fine. So today's experiment is measurement of emissivity of a metal disc. So basically what we shall be doing here, we will be taking a metal disc which is wrapped with a shining piece of metal, I mean, which has relatively low emissivity, and we will try to find its emissivity. Okay. So please go to the next slide.
Yes, sir.
Yes. So the objective is to determine the total hemispherical emissivity of a metal disc at different temperatures. So actually, the emissivity of a disc, it is a function of emissivity of a material, emissivity, absorptivity, I mean all the radiative properties. They are actually functions of wavelength and also the also direction. That means a given surface can emit or absorb radiations differently in different directions, and also and obviously emit or absorb radiations differently for different wavelengths. Okay, so so the most fundamental property of radiation, of any of the properties, is known as the directional spectral property. That means it pertains to one particular direction, which is indicated by the two angles, the polar and the azimuthal angle theta and phi. The theta phi combination, they represent one particular direction, and also correspond and spectral, that is one particular wavelength. So the most fundamental emissivity or absorptivity, that is known as the directional spectral emissivity, and this fundamental property, this directional spectral emissivity, is always equal to the directional spectral absorptivity. But that is something which is difficult to measure, because unless you are doing it with a radiation of a single wavelength, or coming from a single direction in that kind of thing, or receiving over a very narrow range of field of view, so that kind of thing, it's difficult. So what we get basically is an integrated effect of radiation for different wavelengths, and radiation for different in different directions. Okay, so if we integrate this directional spectral emissivity over all wavelengths, then what we get is known as a directional total emissivity. So that means total corresponds to, when I say total, that is opposite to a spectral. Spectral means corresponding to a particular wavelength. Total means corresponding to all possible wavelengths. That means mathematically we integrate it from 0 to infinity. Whatever wavelength is present, its contribution will be taken into account. And if you want to still further generalize it, I mean, when a surface at a certain temperature is emitting radiation, I mean, of course, other than the direction and wavelength, it also depends, the emissivity or how much energy is emitted, that of course depends on the power on the surface temperature. So if we are now interested in the total energy emitted by the surface, then we have to take all the directions also into account. So then, once we have got the directional total emissivity, if we integrate that over all possible directions, then what we get is known as the directional. It is known as the hemispherical total emissivity. Okay. So basically, that is the emissivity which you have used in your heat transfer course mostly. I mean, when you have said that radiative exchange between two surfaces, you have written as sigma epsilon T1 to the power 4 minus T2 to the power 4. That sigma, what we have written, that sigma stands for the hemispherical total emissivity. If it is a directional one, then it is generally indicated by a superscript prime. That means it is written as epsilon prime. And if it is a spectral quantity, then it generally has a subscript of lambda. So a directional spectral quantity will be denoted by. Yes.
Sir.
Yes.
Sir, your voice is cracking, sir.
No, sir. It's actually, I think it's from your end because we can hear it clearly.
Okay. So what we are saying is, so if it is directional spectral emissivity, then we generally denote it by epsilon, write it as epsilon prime with a subscript lambda, and as parameters we write this is the functional parameters are lambda, theta, phi, and of course temperature T. When we make it directional total, then the prime remains, but the subscript of lambda goes, and in the list of parameters, from the list of parameters also the wavelength lambda misses out, so it is a function of theta, phi, and T. And finally, when we are considering all possible directions and all possible wavelengths, then it becomes we neither have the superscript, neither have the prime nor the subscript lambda, and that epsilon is a function of temperature only. I mean, for a given material, and that is what we are measuring here. That is what we mostly use. I mean, for substances like metals, for most metals, directional property is rather weak. Spectral property is there, but not so strong. But there are substances like glass, for example, which has a very strong spectral properties, and because of that we have the greenhouse effect. For example, the glass is transparent to the wavelength of the radiation coming from the sun, because that primarily depends on the temperature. I mean, you might have studied in radiation. I mean, of all such radiations, they will be it will be present over a band of wavelength, but there will be a dominant wavelength which is given by a law known as Wien's displacement law, which tells us that the product at which you get the wavelength at which you get the maximum emission multiplied by the surface temperature, that product is a constant. That means, suppose you get the maximum and that product is a constant, it is something like 2897.6 or something like that. So if the sun is at a very high, since the sun is at a very high temperature, its radiation predominantly will come at a very low wavelength. On the other hand, when the sun rays are coming, it can, at that low wavelength, it can pass through the glass. But when it falls on somebody inside the glass box, for example, then the radiation that is emitted by that object, it is that body has a much lower temperature, so the radiation that is now emitted is at a much larger, I mean the temperature is low, so the wavelength is much larger, and at that wavelength, I mean radiation of that wavelength is not transmitted through the glass, it is reflected back. So that's why the heat that comes in from outside, from the solar radiation, you cannot leave the box, because now it is being emitted by it is absorbed by a different surface which is at a much lower temperature, and now the emission is characterized by the temperature of that surface. So that's why how we get this glass house I mean greenhouse effect. I mean this greenhouse, and the greenhouse actually, it comes from an arrangement for preserving green vegetations in cold countries, where the sun ray comes but cannot leave the glass house. So I mean that is what we also mean when we are talking of greenhouse gas. I mean there, of course, for some different gases, there are different gases like carbon dioxide, etc., which absorb the radiation from the radiation that is coming from the Earth's surface and send it back to the Earth's surface. Okay, so that is why the directional and spectral nature of radiation is important. But for most of our ordinary heat transfer calculations, we need the hemispherical spectral emissivity, and that's what we will be measuring. Okay, so next slide, please.
Yes, sir.
Yeah. So here, what the schematic diagram of the system is that we have two identical discs made of the same metal, but one is they were made of the same metal, mounted on a same base, and having same diameter and thickness. But one of them is painted black, while the other one is covered with a shining metal foil. Okay, so there the only difference would be in the emissivity, because the black surface would be a perfectly radiating surface, so it would have the maximum possible radiation. And now what is done? Both the plates are independently heated electrically. Now they are placed side by side, and side to exactly side by side, so that they cannot see each other. I mean, if they were placed at some angle, or if they were placed facing each other, then there would have been a radiative exchange between them, governed by the shape factor or the view factor. But by placing them exactly side by side, we can ensure that radiation emitted by one surface does not reach the other surface. So there is no coupling of the radiation between the two plates. Okay. So we enclose this, and this whole thing is enclosed in the box to eliminate the convection currents, because whenever there is a temperature difference, there is an unavoidable natural circulation, because there is because of the temperature difference. There will be some buoyancy effect. So you cannot radiation and natural convection. These are two things you cannot eliminate in the moment there is a temperature difference. So here also we cannot eliminate the natural circulation, natural convection, but by putting it inside a box, we ensure that there is very little amount of natural convection taking place, and also there is little effect of stray effects of other convective currents, like some air flowing inside the room and things like that. So those are minimized. So that the radiation becomes the dominant mode of heat transfer. So what is the theory then? Basically, I mean, was this definition, emissivity and these things, this part of radiation, was it covered in your class?
Yes, sir. Radiation.
Yes, sir. Yes, sir.
Okay, fine. Then it's fine. So you know that for the emissive power for a black body is given by the Stefan-Boltzmann law. It's given as EB equals to sigma TB to the power 4.
Yes, sir.
So this is the emissive power, means the amount of energy emitted per unit surface area. So if the black surface has a surface area of AB, then the total energy emitted by the black surface is sigma AB sigma, say, I mean AB sigma TB to the power 4.
Yes,
And at the same time, there is some energy being emitted from the ambient, which is at temperature T infinity, and part of it is being absorbed by the part of which is being absorbed by the by this black surface. So, so a black surface is a perfect absorber also. So any radiation that comes is also absorbed. So the radiation that reaches the surface per unit area is sigma T infinity to the power 4. So the radiation that is absorbed is again given by AB sigma T infinity to the power 4. So the net rate of heat transfer from the black surface to the ambient, that is given by AB sigma TB to the power 4 minus T infinity to the power 4. You have used this relation from high school itself.
Yes, sir.
And in the heat transfer course, you have also learned how this is coming. Okay. Now, if we replace the black surface by a, I mean, even for a black surface, perfect black surfaces are not possible. What we are considered as a black surface is something whose emissivity is very close to 1. So, in reality, we just still include an emissivity factor for the black surface, emissivity for the black surface, which in ideal case should be 1, but in real case it could be something less than 1. I mean, some very high value like 0.95, 0.99, it could be something like this, or for simplicity we can also take it to be 1, but in general we put it like this. So the net heat transfer from a black surface to ambient is given by this last expression, sigma B AB, I mean epsilon B AB sigma times TB to the power 4 minus T infinity to the power 4. Okay. So next, can you go to the next slide?
Sir, one thing.
Yes.
Can you hear me? Sir, here, if we are considering the means EB, I mean epsilon, so that means that we are not considering it as a perfectly black body. So the calculation for that is means done by means the perfect means we are calculating the actual value by the perfect value, right? Then we are getting the EB.
Well, we will see how exactly we are doing it. I mean, here actually we have to make some approximation about what should be the value of epsilon. I mean, so I mean, what can be done? I mean, there are ways in which you can. There are more direct ways in which you can. If you want to find out this epsilon B as well, the value, then you have to actually measure the amount of radiation emitted by the surface, and then you can compare it with say something like what you get by integrating the Planck's emissivity or something. So I mean, what you should be doing, I mean, if you can measure what is the exact energy emitted by the surface, that is the sigma TB to the power 4, and if you know TB, you know the QB. If you can measure QB somehow directly, how much whatever radiation is being happening. I mean,
What is that?
actually, what would have the problem is that if there would always be some convection, so the heat that is being lost, you cannot say that the heat is being even, I mean, to know how much heat is lost once the steady state is reached, that should be equal to the amount, how much equal to the heat that is being supplied. So that way it is not a big problem to know how much heat is being transferred from the plate under steady state condition. But the difficult part becomes to segregate how much part of it is removed by convection and how much part by radiation. So if you want to exactly find out what should be the value of this epsilon b, then what you have to do, you have to keep this surface in vacuum. Keep this enclosure, inside the enclosure you have to maintain a perfect vacuum, or maintain it at a very negligibly low pressure, so that the effect of convection would be very less. Okay.
Okay, sir.
So if you can do that, then you can get the exact epsilon b value. But I mean, this is for a more general situation we are doing this. But when we do the calculation, we will take it to be 1. So that way it does not make much sense. But if you want, you can, if from some other source of information you know that it is not 1 but it is 0.95, you can then put the value as 0.95 or 0.99 and do the calculation. That's why epsilon b is kept here. Okay.
Okay, sir.
So now we go to the next slide.
Yes, sir. Wait. Sir.
Okay. Now if we come to the real surface would not emit the same as much amount of energy. Even if it is maintained at the same temperature, it would not emit as much amount of energy as the black surface. So and the ratio of the two emissions from the two surfaces, that is what emissivity is all about. So here what we are talking about is the emissivity averaged over all directions and all wavelengths. So that is what we are calling the hemispherical total emissivity, and that's what we are measuring. So this hemispherical total emissivity, that would be, so the heat emitted, rate of heat transfer from the heat emitted from the Q emitted from the real surface, that would be given by similar expression as the black surface, only now instead of epsilon b we have an epsilon s, that is emissivity of the surface, which is what we have to find out in this experiment. Okay. So if you go to radiation and the radiation that is absorbed by the real surface, for a surface that is also given by, a real surface is also not a perfect absorber. It absorbs only a fraction of the radiation that is incident on it, unlike a black surface, and the fraction which is absorbed is known as the absorptivity and denoted by alpha. So energy absorbed by the surface is alpha s as sigma T infinity to the power 4. Okay. Now for any kind of surface, the directional spectral emissivity and directional spectral absorptivity, they are equal always, irrespective of the wavelength or irrespective of the direction. But when we average it over the different directions and over all wavelengths, then it is not the emissivity equals to absorptivity. That thing is not valid. It is valid for certain specific conditions. So for when we are talking of a hemispherical total emissivity and hemispherical total absorptivity, they will be equal if one of the conditions when they will be equal is when the radiative properties are independent of wavelength and independent of direction, because then when you are integrating it, this epsilon prime epsilon prime lambda and alpha prime lambda, they are independent of theta, phi and lambda, so they will come out of the integral, and so you will be left with only integrating over the wavelength and direction. So they will be equal. So that kind of a surface is called a gray diffuse surface. Gray surface means when the proper, I mean, this is something you will be asked many times in Viva or interview, but I mean, very often I have found that students are not able to answer it. A gray surface means a surface whose radiative properties are independent of wavelength, and a diffuse surface is one in whose radiative properties are independent of direction. So a gray diffuse surface is one as a surface whose radiative properties are independent of direction and wavelength. So most of the metals they are very close to they are gray, by and large gray diffuse in nature. So here for a gray diffuse surface, even the hemispherical emissivity and hemispherical absorptivity, they are equal. So putting them so using that, I can replace this Q absorbed. I can write the Q absorbed as, instead of writing alpha s as sigma T infinity to the power 4, I can write it as epsilon s as sigma T infinity to the power 4. So the net rate of heat transfer from the gray surface to ambient, that is given by epsilon s as sigma Ts to the power 4 minus T infinity to the power 4. Okay. So now we have an expression for the net rate of heat transfer from the black surface and net rate of heat transfer from the from the other test surface, that is the test surface, whose properties we are denoting by the subscript S. Okay. Now here what we have done, we have purposefully designed the experiment in such a way that the areas of the two surfaces are same. So AB equals to AS, and we would also conduct the experiment in such a way that both the surfaces are maintained at the same temperature, that is TB equals to TS. So then what we are getting, then the QB becomes equals to epsilon B times epsilon B times AS sigma TS to the power 4 minus T infinity to the power 4, and QS is epsilon S AS sigma Ts to the power 4 minus T infinity to the power 4. Okay, so if we now subtract them, okay, there is a printing mistake, typing mistake here. When we subtract it, then this QB minus QS, this will be equal to QB minus QS, that will be equal to on the right hand side, this should be TB to the power 4 minus TS to the power 4. And similarly in the next step also. Okay, so the T infinity to the power 4, that part will no, it's correct. It's correct.
Yeah,
It's
that's
correct.
what I'm thinking.
No,
Actually.
it is correct. It is
We
correct.
just changed it to this side and just divide.
Right. It is correct. It is correct, because now TB and TS, they are same. So it is correct. So what is written here is correct. So QB minus QS equals to this thing. So now, if we know the surface area AS, if we know the ambient temperature T infinity, and if we know the common temperature of the two surfaces TS, and if we know the heat supplied to the black surface and the test surface, then we can write like this: epsilon S equals to epsilon B minus this thing. Now, if we know know epsilon B, and if we can find out this QB and QS, I can calculate the epsilon S. So to know QB and QS, what I do, both the plates are electrically heated. So if I know the voltmeter and ammeter readings corresponding to the circuits of the circuits connected to the two surfaces, so that way I can know what will be QB and QS. QS would be the product of the voltmeter and ammeter reading of the circuit connected to the test surface, and QB would be the product of the voltmeter and ammeter readings in the circuit connected to the black surface. So by knowing the voltmeter reading, the ammeter reading, By knowing the voltmeter reading, the ammeter reading, the surface temperatures, temperature, and assuming some value for epsilon b, we would be able to find out the epsilon s. Okay, so this is the theory undergoing. So is the theory, is this part clear? The theory?
Yes, sir.
Okay. So
So
now
what,
let's go.
as we are considering disk, so there must be a little thickness due to which will there be a radiation in the means the horizontal direction means.
You mean from the edges?
Yes, sir, from the edges.
Yes, actually there would be, but what we are doing, we are considering a very thin surface.
Okay, okay.
Okay, so I mean the
The error is very
the
negligible.
thickness is very small, so there it would be very negligible. And actually, because of those, I mean, if you consider those radiations emitted by the sides, then part of it would be reaching the other surface also. I mean, those complications would be coming in. But generally, what will happen? I mean, okay, I'll discuss it when I go to this to the schematic to the actual setup, the photograph. Okay, so go to the next slide.
Yes, sir.
So basically, this is our setup. This is the setup. You can see this here in the yes, where your cursor is. I mean, so there this is the box in which everything is enclosed. The the disc on the right is the black surface, and the other one is this one is the test surface, which is wrapped with something like an aluminum foil or some such thing. They are both mounted. So on the back side also it is undergoing a radiation. And this is the control panel. So what we have on the control panel, so here, like in the previous day's experiment, these are the heater control inputs. You can see the heater control for the test plate and heater control for the black plate. And this is the main switch. If you go to the picture, yes, this is the main switch through which you provide the power, and then this is the heater control for the power for the test plate. And heater control means basically these are known as dimmer stats. That means they will be calibrated in watts. So you put the setting at some watt, but that is not very accurate, and you do not use that value in your calculation. That is only for a kind of calibration purpose. So if you want to get the repeat reading at a particular condition, you should take the setting to a particular value. So that much will be ensured. But if it shows the value power to be say 10 watt, that does not necessarily mean that the actual power supplied is 10 watt. I mean, it is not a very accurate measurement. The voltmeter and ammeter readings are much more accurate. Okay, so you have to go to the heater. So on the left hand side is the heater control for the test plate, and on the right hand side is the heater control for the black plate. And then there is a so then there is a voltmeter and ammeter and a temperature indicator. The same voltmeter, same ammeter, and the same temperature indicator will be giving you readings for both the test plate and the black plate. But for that you have to use this selector switch, right? So if you use this selector switch, you will get the values. Okay. And So here in the box, you can see that they have been placed just side by side, and just for the aid of visualizing, you have put a glass surface here on the front, but you could have put some opaque surface also, some plywood surface like the other faces also. I mean, you would not have been able to see it during the experiment. You could have seen it before the experiment and then closed it. I mean, it is not important because you are not doing any visual measurement there. Okay. So is the setup clear?
Sir, one thing.
Yes.
Sir, there is a selector switch under the temperature indicator here, and there is
Yes.
another for the under the ammeter. So when we are seeing for the ammeter, then we have to
Yes. I mean, there is a selector switch for each of these readings. So by switching on for the ammeter and for each of these things, we can switch on and get the corresponding readings.
Okay, sir.
Okay.
Okay, sir.
Okay. So now go to the next.
Hello, sir.
Yes.
স্যার বলছি স্যার মানে ব্ল্যাক প্লেট আর যে মেটাল প্লেট ওটার দুটোরই স্যার টেম্পারেচার মানে সেম রাখবো কি করে মানে ওটা
সেম রাখবো কি করে? হ্যাঁ, সেটাকে আমরা পাওয়ারটাকে অ্যাডজাস্ট করে করতে হবে। মানে ওইটাই এক্সপেরিমেন্টের মানে ট্রিকি পার্ট হচ্ছে ওইটাই। মানে আমি একটা ওই এক্সেল দিয়ে আগের দিন যেরকম ওই একটা ওই মানে সেই ডিজিটাল সিমুলেটর যেরকম ছিল সেরকম এইটারও একটা আমি এটা বানিয়েছি, সেটা দিয়ে দেখাবো যে মানে কিভাবে তোমাকে ট্রায়াল এন্ড এরর কিভাবে তোমাকে ওটা করতে হবে সেটা দেখাবো আর কি। মানে ওটা জাস্ট তোমাকে অ্যাডজাস্ট করে করতে হবে। মানে দ্যাটস ওয়াই অ্যাকচুয়ালি ইফ ইউ ডু দিস এক্সপেরিমেন্ট, দিস ইজ আ ভেরি টাইম কনজিউমিং এক্সপেরিমেন্ট। কেননা তুমি একটা পাওয়ার দিয়ে তুমি ইউ হ্যাভ টু ওয়েট ফর সাম টাইম to for both the plates to come to a steady state, and then if you see that they are not equal, then you have to again change one of them. Say if you see that the black surface is showing a higher temperature than the test surface, then maybe you have to reduce the power supply to the black surface or increase the power supply to the test surface, and then again check if it has come. I mean, এই ইকুয়াল করাটা এটা তোমাকে ট্রায়াল এন্ড এরর দিয়ে করতে হবে।
স্যার স্টেডি স্টেটে যেতে গেলে তো মানে অনেকটা বেশি টাইম লেগে যাবে মানে বারবার
তা তো লাগবেই।
এবার স্যার যদি আমি সেটা করতে চাই তাহলে ভিতরে তো সামনে তো কাঁচ দেওয়া মানে এয়ারটা তো ভিতরে পুরো এনক্লোজড অবস্থায় রয়েছে, এয়ার তো এক্সচেঞ্জ
গরম হয়ে যাবে বলছো?
ইয়েস স্যার টেম্পারেচার তো
এটা এনক্লোজড হলেও সেইটা যাতে না হয় বা ওই ভেতরে এই বক্স যেটা আছে বক্সের উপর কিছু ছোট there are a few holes on the top of it. So basically there is some ventilation. I mean that also increases the importance or contribution of the combustion of the convection, but that will prevent the heating of the air inside the box. And actually what will happen, তোমার এই সাইডে তো তোমার যে গ্লাসটা দেওয়া আছে বা এগুলো দেওয়া আছে তার ফলে তোমার খুব বেশি হিটিং হবে না। মানে তোমার যেটা হতে পারে অ্যাকচুয়ালি যে তোমার মানে ভেতরের যে এয়ার টেম্পারেচার, আমরা সেই ক্যালকুলেশনের মধ্যে উই আর নট টেকিং দিস ইনটু অ্যাকাউন্ট, বাট ইন এ মোর অ্যাকুরেট অ্যানালিসিস উই শুড কনসিডার দ্য টেম্পারেচার অফ এয়ার ইনসাইড দ্য বক্স and the temperature of the ambient. So far as radiation is considered, so far as radiation is concerned, it would be because air does not absorb the radiation, so the whatever radiation is emitted from the surface, that will pass through the glass surface and go to the ambient. But the convection will take place in a local manner, so that will be determined by the temperature of the air inside the box. I mean, if there is a significant difference, if there is a significant heating of the air inside the box, then the temperature, the surrounding temperature for convection and surrounding temperature for radiation, they would be somewhat different. But here we do not take that into account.
Okay, sir.
Okay. So next slide. So these are basically the specifications. So what we have, this is the enclosure size. You can see that Enclosure size is 58 centimeter, that is 580 millimeters long, 350 millimeter wide, and 350 millimeter high. High enclosure, and the test plate and black plate both have a diameter of 160 millimeter. Both the heaters are nichrome strip wound on a mica sheet and sandwiched between sheets. I mean the nichrome strip is sandwiched between two mica sheets. So that is how, I mean, the heating arrangement is very much like what you have in an electric iron. And there are 3 thermocouples of chromel alumel. So chromel alumel, I mean, these are different alloys. I mean, I don't know whether you have read about thermocouples in physics anywhere, but in the next year, when you are in 3rd year, then you will be reading, then you will be doing a course on 3rd year 2nd semester. You will be doing a course on instrumentation and measurement. There will be reading in detail about the different types of thermocouples, and you will also be doing experiments on that. So this basically, you know, the thermocouples, they act on the on which effect. There is what is the working principle of a thermocouple?
I think it's the Seebeck effect.
Seebeck effect, that's right. What is Seebeck effect?
Sir, if we give some temperature at one end of 2 metal joints, then there will be a voltage will be generated.
Yes, yes. If 2 ends of maintain, if there is a temperature difference between two, I mean, if you have 2 dissimilar metals joined together, and at 2 ends of it maintain at different temperatures, then this temperature difference will lead to will generate an EMF between which will be directly proportional. So if you're measuring the EMF, you can get the temperature. And what is the opposite of the Seebeck effect?
The Peltier effect.
Yes. So there, what happens? If you maintain a voltage difference, that will create a temperature difference. So that is one way in which one way of cooling. I mean, that is called thermoelectric effect, thermoelectric cooling. I mean, that is one way of doing refrigeration. Okay. Okay. So here the chromel alumel means, I mean, these are different. When you are making thermocouples, you are making thermocouples with different alloys. I mean, different materials, and depending on the combination of materials, they can be used for different temperature ranges. You have different things like this chromel alumel, so which are 2 alloys. Then you have iron constant and copper constant, and so different combinations of materials, they can test temperatures in the different ranges, and these are also known by certain alphabets. I mean, this chromel alumel, for example, the copper constant and thermocouples, these are known as K type. There's K type, R type, N type. So these are different types of thermocouples. I will study about them in your instrumentation course. Okay. So which type of thermocouple we use, that depends on the on the range of temperatures that we expect to get. So here we are typically getting somewhat low temperatures, but not very much different from ambient temperatures. So we are using chromel alumel. Okay. So then there is thermostats, which are whose ratings are 0 to 2 ampere and 0 to 260 voltage. Then digital voltmeter and digital ammeter, digital temperature indicator with room temperature compensation. Room temperature compensation means when you are very often when you are measuring the thermocouple, one end of it is exposed to the ambient temperature. So the Seebeck effect is basically giving you the temperature difference between the between the two ends. So one end, if it is maintained at ambient temperature, so what you are getting is, if you are getting 10 degree, I mean, if you are getting an a voltage generated corresponding to 10 degrees centigrade, it only means that the difference between the hot junction and the cold junction of the thermocouple, that is 10 degrees Celsius. It is not so if the cold junction is maintained at say ambient temperature, then it is ambient temperature plus 10 degrees Celsius. So here the ambient temperature correction is done, and the actual value is given, so that you can so whatever value is given, that is after doing the ambient temperature correction. Okay, so that you don't have to add the ambient temperature separately. That's how the indicator is calibrated. Okay. Okay, so now go to the next slide. Okay, so this is the procedure. So how will we do it? So first you give the power supply to the temperature indicator and adjust the readings in it equal to room temperature by rotating the compensation knob. Normally this is pre-adjusted. Normally you don't have to do it. I mean, so to do the room temperature setting, this is called a pre-adjustment step. Normally this is done once for all, and I mean, for a long time this is valid. So every time you do the experiment, you don't do this. This is already done, because this is a very time consuming thing. So then select the proper range on the voltmeter or ammeter. That means you choose the range in which you expect the current and voltage values to get. Gradually increase the input to the heater to the black plate and adjust it to some value, say like 30 watt, 50 watt, 75 watt, like this, and simultaneously adjust the heater input to the test plate slightly less than the black plate. Why? Because the black plate has a higher emissivity, so it will have a higher rate of heat transfer. So if you want to measure the same temperature in case of the test plate, with the same temperature difference, the black plate would be losing more heat, so it should be supplied with more heat also to achieve steady state. So you always adjust it in such a way. I mean, we are talking of how do we adjust it, the trial and error, but one intelligent thing about the trial and error is that thing that you can adopt is that the heater the power input to the test bed should be slightly less than the power input to the black plate. So if you just try to do the other way around, or if you keep the power input to both of them same, you will never achieve this equality. Okay, so check the temperature of the two plates and adjust the thermostat so that the two plates are maintained at the same temperature. Okay, ideally we should check it only after the steady state has been reached, but because both the plates have the same size, so they have the same material, everything is same, so they have similar thermal capacity, so you can so their rate of change of temperature, that should also be more or less similar. So even before it achieves steady state, you can, after some time, if you start seeing that there is a lot of difference between the two readings, then you can start making changes even before the steady state is reached. So it requires trial and error and more than 1 hour of waiting before steady state is achieved. So here, because the heat transfer by convection is very low, so the steady state is achieved very slowly. So you have to wait for more than 1 hour. So typically, when the experiments are done in the physical class, because you have only 2 hours of class, so what is done? These readings are generally, initial readings are at least one set of readings. They are set much before the class, so that immediately after coming to the class, you can take the reading, and thereafter it is changed, and so it takes some more time. So you have enough time for 3 or 4 readings. Okay. So after the steady state is achieved, record the readings of V1, I1, V2, I2, T1, T2 and T infinity. 1 subscript 1 and 2, they correspond to the black plate and the test plate. So the voltage across the heater for the black plate, current supply to the heater connected to the black plate, and the temperature of the black plate, and similar things for the test plate. These are the 6 things plus the ambient temperature. So these are the 7 things that you are measuring, and then the process is repeated for various surface temperatures in increasing order. So how we will achieve the various surface temperatures? By increasing the power supply.
Yes,
And you should move in one direction only, because that way the attainment of steady state will be quicker. Say for example, it is already at steady state corresponding to say 30 watts of power. So when you change the power to from 30 to 45, it will definitely take some time to reach steady state, but it will take much less time compared to what it would have taken if you had directly changed from 0 to 45 watts. So you start with a lower value of power and gradually increase the power. Okay.
okay, sir.
So this is the procedure. So now go to the next slide, please. So there are certain, as usual, there are certain precautions. Use stabilized AC single phase supply. If it is not stabilized, if there is too much of voltage fluctuation, then the steady state, achieving the steady state will become difficult. Always keep the thermostat at 0 position before starting, so that at the start there is a big voltage surge, so that should not lead to a sudden increase in current supply. So first you switch on and then start increasing the power.
Yes, sir.
Gradually increase the heater input. See that the black plate is having a uniform layer of lamp black. So here basically lamp black, that means the soot from the lamp, that you are painting it over the black surface. So it should see that it is as uniform as possible. It should not be clumpy and lumpy at different places. Okay. And never put the heater selector switch at off position, that is at the intermediate position. So always keep the heater selector switch either in the either in the test plate position or in the black plate position. Okay. So
Can I
next,
go to sir, one second.
Yes.
Sir, that means the selector switch means this one should not be, means between this and this we cannot means take it in the mid position, like
you should not keep it in the mid position. It should always be
in
because if you are putting it in the mid position, then it may mean that heat is being supplied to both, and then everything becomes out of control. I mean, you do not know exactly what is happening.
Yes, sir. Yes, sir.
Okay.
Yes, sir. Next.
Okay. So then these are the observation tables. So the 7 for each set of runs, you have to make 7 observations. And then go to the next slide.
Yes, sir.
Okay. So now the sample, the calculation. So how we will calculate? Calculate the power input to the test plate. So you have got the V1 and I1 values. So you calculate Q1, the power input to the test plate, and power input to the black plate. And here we are considering that radiation is taking place from both the faces. That's why we are multiplying this area by 2. So to calculate the area of each plate, and as I said here, we assume the epsilon b to be equal to 1. We do not know. It is certainly not 1, but it is very close to 1. It could be 0.95, it could be 0.99. That would make some difference. Of course, it will make a difference in the reading, but because we do not know, that is a source of error and uncertainty.
Hello, sir.
Instead of putting any arbitrary value, in the name of making it more realistic, having no idea about what should be that value, we just put the ideal value. If you have to put a correct estimate of this, then you have to do the same experiment in a vacuum chambers with the so that all the heat transfer will actually be from radiation only, and you get the value of epsilon b. But that would be very cumbersome, because time to time you may have to paint the plate with this lamp black. I mean, and every time you give a coating of lamp black, the condition changes. You have to again take it back to the vacuum chamber and do the experiment and calibrate its value.
Yes.
Okay.
Yes, sir.
So now, if you have when you have done that test for different sets, that is, you have used for different power levels, then for different power levels you would get the different temperatures of the surface, and different emissivity values also you will be getting, and then you can find out what should be the
Emissivity of the test.
how emissivity varies with temperature. Okay, so this is what you have to do. I will go to the next slide.
Yes, sir. Yes.
Anything else?
Sir, no, sir. There is no.
This is the last slide.
Yes, sir. I think so. Yes, sir. It's the last.
Okay. Okay, fine. So this is what you have to do, and then so again in the report part, that should be exactly same to what you have done. The report part should be exactly same to what you did in the previous report. That means you have to. I will upload the. Sorry, I will upload the lab sheet. I will upload the schematic diagrams. You don't have to do anything. You have to just attach that. Attach that lab sheet in your, and the schematic diagrams in your PDF file. In your PDF file. Only the observation table you have to make it with hand, and put the results that I will send you, and also the calculation tables. Calculate the results for all the cases, but sample calculation for only one power level. The complete steps of the sample calculation for only one power level, and finally the graph of epsilon versus t. So that way only, and of course the cover sheet at the top. So that is all that you have to do in your experimental report. You should not put anything else. I mean, okay. So Swapnil, can you just go to the other folder where it is that digital simulation? Yes.
Sir,
yes.
Let me download it first, because it
yes.
Okay, sir.
Yes. So I will not be able to operate it. I will just tell you. You have to run it by yourself. Okay. So
Yes.
what you have to do, I mean, this is a little more complicated than because this will, here a nonlinear equation will be solved. So you just remember one thing. You just remember this. You just note down these values, and then again, as in the previous day, this only the shaded boxes are where you have to give the inputs. So you just note down these values and remove them.
Okay, sir. Okay, sir. Sir, we will get the values from this simulation, or you will be providing us like the previous one?
No. The report you will write from the actual simulation, experiment that we had done previously. Here,
Okay.
this is only for your practice. I mean, this is supposed to be a substitute for that, but for that we require more tuning and more.
Yes, sir.
I mean, it requires some fine tuning and comparing with all the results that are available and things like that. So that I have not been able to do. I mean, because I made this just in the last week. I mean, in the during your exam time, because when suddenly the classes were had to be suspended. So that time I just made it. I have made it only for these two. So let me see whether I can do it for the others also. So you just
Okay, sir.
remove these values. Just remember these values. I mean, arbitrarily. So 13. So I mean, let this column be there. The C column, let it be there. You just remove the values from the B column. This 15 and 22 also. I mean, you can remove this also, but that is.
Sir, I will keep it at ambient 39, then and then remove the test plate volumes and this one, right? Hello, sir. Hello. Hello, sir. Can you hear me? Hello, sir. Am I audible?
Yes,
Yes,
yes.
Swapnil, you are audible.
So you just remove this 15 and 22.
Hello, sir. We cannot hear your voice actually, sir. So now it's sir. We are okay, sir. Hello, sir.
Sir has left, I think.
Okay, I guess due to some network issue. Let him come back. Raj sir, क्या आया? Sir, can you hear me?
Yes, sir, John.
Actually,
Yes, I can hear. Actually, because I have to. My net connection is also through the phone, so I have to pick up a phone, so it
okay,
got
sir,
disconnected.
okay, sir. Not an issue.
So just yes, go to this thing.
Yes, sir.
Yes. So. So you just remove these columns, these rows 16 and 17 also. I mean,
16 and 17 means, sir, these two.
this plate temperature and plate temperature rounded off these values also.
Black plate temperature, to?
Black plate.
Sir, can you see my screen?
Yes, I can see your screen. আচ্ছা পুরোটা দেখতে পাচ্ছি। হ্যাঁ, ব্ল্যাক প্লেট ওই কলামগুলো ওখানে যা ওই প্লেট টেম্পারেচার ওইটাকে তুমি রিমুভ করে দাও। দেখি তাতে কিছু গন্ডগোল হবে। আচ্ছা ঠিক আছে, ছেড়ে দাও তুমি।
এক সেকেন্ড স্যার। হ্যাঁ স্যার বলুন। স্যার আমরা তো এগুলোতে শুধু ভ্যালু দিতে পারবো তো?
হ্যাঁ, তোমরা এগুলোতেই ভ্যালু দিতে পারবে, কিন্তু এখানে একটু অন্য জিনিস, এখানে আর একটু বেশি করতে হবে। তুমি আর একটু পুরো স্ক্রিনটা একটু মানে পুরো এটা আর একটু নামাও, মানে আমি এই এক্সেল এর ফাইলটা একটু দেখি। টেম্পারেচার রাউন্ডেড টু ফার্স্ট প্লেস। আচ্ছা, এইটাতে একবার এই কলাম 16 একবার একটু করে দেখো তো, ক্লিক করে দেখো তো কিছু মানে কোনো ফর্মুলা দেখাচ্ছে না কি দেখাচ্ছে? এই
স্যার নাম্বারটা দেন।
রো সি B16 B16 এ
হ্যাঁ স্যার ক্লিক করেছি। 9 এই ভ্যালুটা দেখাচ্ছে শুধু।
জাস্ট ভ্যালুটা দেখাচ্ছে তো? ঠিক আছে, তাহলে এগুলোকে ডিলিট করে দাও।
আচ্ছা,
ওইটাকে মানে 17টা ডিলিট করো না, এটা ডিলিট করে দাও।
হ্যাঁ স্যার করে দিয়েছি।
বেশ। আচ্ছা, এবারে ধরো তুমি ওই যেমন ভ্যালুগুলো তুমি ওখানে দেখেছিলে, এবারে তুমি ওই ইনপুটটা দাও। তুমি দেখতে পাবে কিভাবে। আচ্ছা, অ্যাম্বিয়েন্ট টেম্পারেচারটাকে তুমি ইনপুট, ঠিক আছে 39 ইনপুট আছে, ঠিক আছে থাক।
হ্যাঁ স্যার।
আচ্ছা, এবারে তোমার এই ডিমারস্ট্যাট ইনপুট টু দ্য ব্ল্যাক প্লেট আমরা কত দিয়েছিলাম? 22.5 বা এরকম কিছু ছিল বোধহয়, না? যাও কিছু একটা দাও, কিছু এসে যায় না। তুমি কিছু
Okay.
একটা ভ্যালু দাও।
আচ্ছা স্যার, ঠিক আমরা তো ওয়াটে দিচ্ছিলাম, তো স্যার অ্যাকর্ডিং টু মানে ওখানে যে ভ্যালুস গুলো ছিল সেগুলোই তাহলে দিই, লাইক আই গেস বেশি ছিল, তো এইটাতে স্যার ফার্স্টে 30 দিচ্ছি।
বেশ 30 দাও,
আর
30
উপরে
দিলে তো?
হ্যাঁ
আচ্ছা 30 দিলে এবারে 30 দিলে রিডিংটা আসছে না কেন? টেস্ট
টেস্ট প্লেটের ভ্যালু একটু কম দিতে হবে আশা করি, মানে
ও আচ্ছা, এখানে রিডিংটা আসছে। আচ্ছা ঠিক আছে, তুমি ব্ল্যাক প্লেটারটা দিয়েছো, তোমার ব্ল্যাক প্লেটের রিডিং গুলো আসছে তাই না? তাহলে ব্ল্যাক প্লেটের ভোল্ট মিটার মিটার রিডিং গুলো আসছে তাই তো? দেখো
ভোল্ট না, আচ্ছা দেখছি স্যার।
ব্ল্যাক প্লেটে এসেছে, এই যে ব্ল্যাক প্লেটে এসেছে,
হ্যাঁ স্যার।
ঠিক আছে। আচ্ছা এইবারে তুমি এই যে দাঁড়াও, এই যে টেস্ট
স্যার টেস্ট
আর একটু নামো, ব্ল্যাক প্লেটের জায়গাটা যাও।
হ্যাঁ স্যার।
আচ্ছা এই যে এই টেম্পারেচার ফাংশন যেটা আছে, এইটাকে তুমি এই সেলটাকে ক্লিক করো, মানে
Yes,
হ্যাঁ
sir.
এটা করে এবারে এইখানে একটুখানি তোমাদের মানে জাস্ট এতে যেতে হবে, তোমার ওই ওই দেখো তোমার ওই এই কন্ডিশনাল, সরি তুমি এই ডেটাতে যাও।
কোন স্যার, মানে ডেটা বলতে?
ডেটা ফিল্ডটায় উপরে,
হ্যাঁ স্যার বলুন।
হ্যাঁ ওইটা ক্লিক করো।
স্যার টেস্ট প্লেট নাকি ব্ল্যাক প্লেটের সেকেন্ড ভ্যালুটা?
না, ওই তুমি যেখানে এটা করেছো, মানে তুমি ওই সেলটাকে তো তুমি ক্লিক করেছো।
হ্যাঁ স্যার।
না ওখানে নয়, তুমি যে সেলটা ওই হ্যাঁ এইটা এই টেস্ট ফাংশনটা ক্লিক করে এবারে তুমি দেখো তুমি ধরো একটা জাস্ট মিনিট। আচ্ছা এই কন্ডিশনাল ফরম্যাটিং নয়, তুমি এই ডেটা হোম এর বদলে তুমি এই ডেটা ট্যাবটাকে ক্লিক করো, এই যে উপরে একদম টপ রিবনে, হ্যাঁ ওই ইনপুট ইনসার্ট, এই হোম ইনসার্ট পেজ লেআউট ডেটা যাও।
আচ্ছা স্যার দাঁড়ান এক সেকেন্ড, ডেটা স্যার ডেটা কোথায় আমি ঠিক?
এই যে ফর্মুলাস।
ও আচ্ছা আচ্ছা, এক সেকেন্ড দাঁড়ান স্যার।
আর উপরে ডেটা ট্যাবে ফাইল হোম
সরি একটু খেয়াল করিনি আর কি।
হ্যাঁ রাইট, এখানে ডেটাতে জাস্ট মিনিট, আমি এই যে ডেটা ট্যাবে গিয়ে এবার তুমি এই দেখো এই হোয়াট ইফ অ্যানালিসিস একটা আসছে, দেখো।
হোয়াট ইফ অ্যানালিসিস, হ্যাঁ স্যার।
হ্যাঁ এটা ক্লিক করো, হ্যাঁ করে এই গোল সিক মাঝখানে সেকেন্ড যেটা আছে গোল সিক,
হ্যাঁ স্যার।
মানে বেসিক্যালি এটাতে তোমার ওই একটা নন লিনিয়ার ইকুয়েশনকে তোমার সলভ করো। তুমি গোল সিকটাকে ক্লিক করো।
ইয়েস স্যার।
গোল সিকটা ক্লিক করার পর কি হলো, মানে সেট সেল, মানে তুমি ওই B25 এর যে ফাংশনটা আছে সেইটাকে তুমি তুমি কি ভ্যালু দিতে চাও, বেসিক্যালি ওইটাকে ওই ইকুয়াল টু দ্যাট ইজ ইকুয়াল টু 0 করে আমি ইকুয়েশনটা সলভ করার চেষ্টা করছি। এই যে ফর্মুলাটা যে দেওয়া রয়েছে, দিস ইকুয়াল টু 0 করে আমি টেম্পারেচারটা বার করার চেষ্টা করছি। সো তো টু ভ্যালুটাকে 0 দাও।
হ্যাঁ স্যার।
আর বাই চেঞ্জিং সেল, মানে যেটা তোমার ওই মানে ওই সেট প্লেট টেম্পারেচারের যে ভ্যালুটা আছে, মানে তোমার এই B23 টাকে ক্লিক করো, বাই চেঞ্জিং সেলের জায়গাটাতে ওটা তুমি B23 টা লেখো।
ওকে স্যার।
B23 লেখো ভাই, হ্যাঁ এবার তুমি ওকে দাও।
সেন্সর B23, হ্যাঁ ঠিক আছে স্যার, ওকে করলাম।
হ্যাঁ এই যে করে যে তোমার কারেন্ট ভ্যালু তোমার দেখো চেঞ্জ করে তুমি একটা ভ্যালু পেয়ে গেলে। এটা সলভ করে তোমার এই যে 114.5 114.48 এরকম একটা ভ্যালু হলো, তুমি সেটাকে রাউন্ডেড অফ টু ফার্স্ট প্লেস করে তুমি 114.5 পেলে, ঠিক আছে। এটা হচ্ছে তোমার টেস্ট প্লেটের, সরি ব্ল্যাক প্লেটের এটা পেলে। এবারে তুমি সিমিলারলি ওই টেস্ট প্লেটের জন্য তুমি আরেকটা মানে স্লাইটলি টেস্ট প্লেটের জন্য তোমাকে কি দিতে হবে, স্লাইটলি কম পাওয়ার ইনপুট দিতে হবে।
আচ্ছা, তো স্যার টেস্ট, স্যার এটা ওকে করলাম স্যার। টেস্ট প্লেটের
হয়ে গেল। এবারে যে টেস্ট প্লেটের যে এই ডিমনস্ট্রেট ইনপুট যেখানে আছে, এখানে তুমি টেস্ট প্লেটে এটা 30 দিয়েছো, তাহলে ধরো তুমি হ্যাঁ 27 দিলে,
হ্যাঁ স্যার।
হ্যাঁ 27 দিয়ে তোমার এখানে আবার এই ভ্যালু গুলো এলো। তোমার এই যে এখানে এখানে এলো, তো তোমার এই যে ফাংশন, এই ফাংশনটা টেস্ট ফাংশনটা ক্লিক
হ্যাঁ
করলে,
করেছি।
করে আবার তুমি ওই হোয়াট ইফ অ্যানালিসিসে যাও।
হ্যাঁ স্যার।
হোয়াট ইফ অ্যানালিসিসে গিয়ে সেট সেল B18 টু ভ্যালু 0,
হ্যাঁ স্যার।
আর ওই তোমার এই টেম্পারেচারটা কোথায় আছে দেখো, তোমার এই প্লেট টেম্পারেচার B16।
হ্যাঁ স্যার।
হ্যাঁ, তুমি ওই বাই চেঞ্জিং B16 মানে এটা তুমি ওই টেম্পারেচারটাকে চেঞ্জ করে ও ইটারেটিভলি সলভ করে তোমার বার করবে। করে দেখো তোমার এই যে এলো, এসে তুমি দেখছো 140.1 হচ্ছে, মানে তার মানে তোমার এটাতে তোমার টেস্ট প্লেটের টেম্পারেচারটা বেশি হয়ে গেছে তোমাকে, সো ইউ হ্যাভ টু গিভ আ লোয়ার পাওয়ার আউটপুট।
হ্যাঁ, তাহলে আমাকে একটু কম দিতে হবে। তো আমি
হ্যাঁ, আর একটু ওই তুমি ব্ল্যাক প্লেটের ওটাকে ফিক্সড রেখে তুমি আবার টেস্ট প্লেটের পাওয়ারটাকে আর একটু কমিয়ে দাও।
স্যার এটাকে আপাতত ধরুন 23 20 স্যার 20।
তুমি এটা করো, এইভাবে ট্রায়াল এন্ড এরর দিয়ে একটু করো, মানে আমি জাস্ট 1 মিনিট আসছি।
ওকে স্যার। ওকে, এখনো বেশি আছে না, লাইক 20 করতে হবে, বুঝতে পারছি। তো এর আগেরটা 10, হ্যাঁ আশা করি এবার ঠিক হবে। অনেকটা কাছে এসছে, আর একটু কাছে আনতে হবে। তো টেস্ট প্লেট 19 what if analysis, এটা 0 B6 স্যার 1 ডিগ্রি।
হ্যাঁ, এবারে তোমার
স্যার 120 তে গিয়ে বেসিক্যালি ঠিক আসছে,
ওকে ফাইন,
মানে 20 তে 15 মতো আসছে আর কি। স্যার আমাদের কি ভোল্টেজটা তো স্যার মানে ওই মানে কোনো মানে মানে তার লিস্ট কাউন্ট কত স্যার? হ্যালো স্যার।
হ্যাঁ ঠিক আছে, কিছুটা তো ডিফারেন্স আসবে। ওহো,
এক সেকেন্ড দাঁড়ান, আমি দেখাচ্ছি। হ্যাঁ স্যার বলুন।
হ্যাঁ 20 দিয়ে কত এলো?
স্যার 20 দিয়ে 115 মতো আসছে। এবারে যদি ওটা 19 করি তাহলে স্যার অনেকটাই কমে যাচ্ছে, মানে 112 মতো আসছে। তো আই গেস
ওকে ফাইন,
14 ঠিক আছে।
ঠিক আছে, এইরকম ভাবেই তুমি মানে ডিপেন্ডিং অন ওটার রেজলিউশন কত থাকে, মানে যদি তোমার সাফিসিয়েন্টলি হাই রেজলিউশন থাকে তুমি ধরো 19.5 নিয়ে হয়তো করতে পারবে।
লিস্ট কাউন্ট আমাকে জানতে হবে যে মানে ওই রিডিংটা কতটা লিস্ট কাউন্ট দিতে পারছে, লাইক
হ্যাঁ, লিস্ট কাউন্টটা কত নিতে পারে সেইটা দেখে সেইভাবে, মানে তোমার তোমার এই এটাতে এক্স্যাক্টলি এইভাবেই জিনিসটা হয়, ঠিক আছে। মানে আমি এক্সপেরিমেন্টের সময় মানে এই যে তুমি এই যে ট্রায়াল এরর যেটা করছো, তখন জিজ্ঞেস করছিলে ইউ আর আস্কিং হাউ টু গেট দ্য টু টেম্পারেচার সেম, দিস ইজ দ্য এক্সাক্ট ট্রায়াল এন্ড এরর প্রসেস দ্যাট ইউ হ্যাভ টু ডু। Only thing is that it will take much more time in the physical world, because here you are just doing solving an algebraic equation. So this is how it happens. ঠিক আছে,
ক্লোজ আসছে যদি 19.7 নি অ্যাকচুয়ালি।
হ্যাঁ ওইটাই, সেটা তুমি দেখতে হবে। তুমি মানে ইভেন তোমার এটাও হতে পারে যে তুমি এখানে যে তুমি এই টেম্পারেচার যেটা নিচ্ছ, একটু রাউন্ডেড অফ টু ফার্স্ট প্লেস অফ ডেসিমাল করছো, তোমার মানে ওখানে রিডিং এ তোমার ফার্স্ট প্লেস অফ ডেসিমেল অবধি আছে, কিন্তু সেটা তোমার মানে তুমি কতটা ক্লোজ তুমি দিতে পারছো সেটাকে দেখে আমি তোমার রিডিং গুলো তোমাদের পাঠিয়ে দেবো, সেটা দেখলে তোমরা বুঝতে পারবে যে কোন লেভেল, মানে কি লেভেল অফ রেজলিউশনে তুমি যেতে পারো। মানে
হ্যাঁ,
সার্টেনলি নট বিলো মানে এর থেকে আর ছোট, মানে সেকেন্ড প্লেস অফ ডেসিমেল ডেফিনেটলি হবে না, কিন্তু মানে এরকম ভাবে তুমি কতটা ফাইনাল রিডিং এ যেতে পারো সেটা দেখে তুমি করছো, মানে মানে তুমি ওই ভ্যালুগুলো মানে দিস ইজ হাউ ইট উইল গো অন।
হ্যাঁ স্যার, টেম্পারেচারটা বেসিক্যালি টেস্ট প্লেটের 19.6 থেকে 19.7 এর মধ্যে কোনো একটা হবে, কিন্তু স্যার মনে হয় তার মধ্যে তো মানে ডাবল ডেসিমেলে মনে হয় যেতে পারবো না, তাই আর কি।
হ্যাঁ, ওই রকম তোমার যেটুকুনি ডিফারেন্স থাকবে সেই ডিফারেন্সটা নিয়েই তোমায় কাজ করতে হবে। মানে ওই 114.5 আর 114.6 অ্যাকচুয়ালি ক্যালকুলেশন যদি ধরো তোমার এরকম রিডিং এ এক্সাক্ট সেম করতে না পারো, দেন ইউ হ্যাভ টু টেক অ্যান অ্যাভারেজ অফ দ্য টু ভ্যালুস। মানে ইভেন এক্সপেরিমেন্ট করার সময় তো হতেই পারে যে তুমি সেট করতে পারছো না নবটাকে ঘুরিয়ে, মানে এক্স্যাক্টলি সেম সেট করতে পারছো না, তখন তোমাকে ওই নবটা ঘুরিয়ে, মানে তখন তোমাকে ওই দুটো ভ্যালুর অ্যাভারেজ দিয়ে, যেমন ধরো এখানে তোমার এই 114.6 আর 114.5 আসছে, সেখানে তুমি ওই দুটোর অ্যাভারেজ নিয়ে 114.55 এরকম কিছু একটা ভ্যালু নিয়ে বা করে তুমি কাজটা করলে, ক্যালকুলেশনটা, তাহলে এরপরের ক্যালকুলেশন গুলো তুমি করলে। সো দিস ইজ হাউ ইট ওয়ার্কস।
Yes, sir.
ওকে,
স্যার এমনি তো মানে টেম্পারেচার টু দি পাওয়ার 4 এ আছে, মানে খুব এরর যদি মানে 0.1 ও হয় তাহলে তো স্যার মানে স্কোয়ার করলে তো আরো ছোট হয়ে যাবে, মানে টু দি পাওয়ার 4 করলে সেটা তো খুব নেগলিজেবল।
মানে হ্যাঁ হ্যাঁ, ওটা খুবই নেগলিজিবল হয়ে যায়, কারণ 0.1 তো ওখানে তোর 0.0001 মতো, তো মানে আরো
not only that সেটা আবার মাল্টিপ্লাইড হবে উইথ স্টিফেন বোলজম্যান কনস্ট্যান্ট,
স্যার আরো ছোট।
অনেক ছোট হবে, কিন্তু আবার তোমার ওই এরিয়াটা ইন মিলিমিটার স্কোয়ার হবে, সেটাকে তুমি যখন মিটার স্কোয়ারে করছো সেটা আবার একটা ওকে, মানে সেটাও একটা ছোট হবে। সুতরাং এরারটা তোমার খুবই ছোট ভ্যালুই আসবে, মানে তুমি ওই একটু থাকলেও তোমার খুব বেশি তফাৎ হবে না। মানে তুমি ওই এক্সপ্রেশন থেকে তুমি বার করতে পারো যে কিরকম তোমার এরারটা আসতে পারে। ঠিক আছে,
হ্যাঁ স্যার।
ইয়েস।
okay. So this is the experiment. Okay, so this is all about it. So so you can stop the recording now.
Yes sir. স্যার এক্সপ্রেশন কি বন্ধ করে দেবো? Okay
The presentation বন্ধ করো, আর Raj, you can also stop the recording.
I'm stopping the recording.
yes sir.
So you do one thing, you just if you put the recording this